I'd like now to talk about the synthesis of acid anhydrides, and this method here is something that can be used to make either symmetric or asymmetric acid anhydrides. The first step involves carboxylate ion formation, and what we're doing here is we're taking some kind of base and removing the proton from the carboxylic acid. Carboxylic acids, first and foremost, are acids, which means it's easy to remove the proton from a carboxylic acid with some kind of base. In the next step, we take the carboxylate ion and we react it with an acid chloride in a reaction that is ostensibly a basic type mechanism. Earlier when I was talking about reactivities, I mentioned there were three kinds of mechanisms that we were concerned with most of these carboxylic acid derivative reactants. The first one was acidic, the second one was neutral, and the third one is basic. The one we're looking at is going to be considered to be basic because we have something negative above the arrow. So something clearly negative is reacting with our carboxylic acid derivative. In this case it's the carboxylate ion, so it's going to follow this particular mechanism. I'm going to show you how to apply this mechanism in this particular instance. Alright, let's see how we might form one of these, and I'll also give you a discussion of the mechanism as well. So let's say you had wanted to make this particular anhydride. The first thing you would do is you would take acetic acid and you would treat it with sodium hydroxide or some kind of other base and get the carboxylate ion, and this would be plus Na plus and H2O. So the mechanism for that is fairly simple. It's just going to be the OH minus coming in and pulling the hydrogen off the carboxylic acid to give a carboxylate ion. In the next step, what we're going to do is we're going to take this carboxylate ion and we'll react it to form the other side of our acid anhydride. And what we're going to need here is the butanoyl chloride. And that will give us our product. Alright, let me show you the mechanism for this. First of all, I'm going to rewrite this, and I'll rewrite it with the benzoyl chloride here, and I'll put the carboxylate ion above the arrow so it looks more like what I've got. And that will be our product, and Cl minus as well. Alright, so as I said, we can identify this as being a basic mechanism by looking at the fact that we have an acid chloride here, and then we've got a carboxylate ion above the arrow, and that's going to result in this X group, which is the whole carboxylate ion, replacing the Y, and we'll get Y negative as a side product as well. Alright, let me show you how that works in this instance. I'll repeat the pattern over here so you can see it. Alright, so there's our pattern. You can see that this is going to be Y. This whole thing is going to be X negative. And then you can see that this is going to be the X group. I'll put R's here just so we don't get confused. And then you can see how else this comes out, and the Y minus will be the Cl minus over here. Alright, so let's see how that works for the mechanism. So this comes in, attacks the C double bond O, electrons jump up on the O, and this is the way it always goes for a basic type mechanism. And you'll see this pattern again and again. And then we will have the negative come down and kick out the leaving group. And you can see that's how we get our product, which can easily be written as the way I've got it up here. I've just left it like this because this is the way it was in the diagram. And then we get Cl minus as a product as well. What's important for you to see is that this entire thing, which is X minus, ends up replacing the Cl. And you'll see this pattern occur again and again when we go through these.